Good day, everyone. My name Igede Susrama Mastiasa, and today I will be presenting our research on automatic analysis of spam quality using WGAN and transfer learning. Our project, spam quants. I am to revolutionize spam quality analysis using cutting edge of teknik AI teknik. Next. Our team consists of dedicated professional with diverse expertise. Our machine learning engineering consists of Anindya, Daniel, and Rizky. Then our data scientists, Christina and Ayu, also play a pivotal role in this project. We will delve into the behind our research planning and implementation. To provide a comprehensive understanding, we have prepared a video that showcases the step we undertake in our research. Later, I will be assisted by Daniel to explain further. Next. In spam quality analysis, we have a problem that traditional spam quality analysis in laboratories is time consuming and often hampered by different opinions from each expert. This inefficiency can delay crucial medical diagnosis and treatment. Our solution involves developing automatic system for spam quality analysis using machine learning. By leveraging transfer learning techniques, we can implement more robust machine learning model and overcome data scarcity through augmentation technique. Next. Before this research, several studies in spam analysis have been made, and to understand the current landscape of spam analysis technologies. From this picture, it can be seen that the state of the art of the research I have done is based on morphology and motility. Based on morphology and is research, cacah spermatozoa menggunakan background segmentation and boundary detection. Next, teratospermia classification based on the shape of sperm edge using Otsu threshold and decision tree. Based on morphology in research and based on motility in as in research, abnormality the determination of spermatozoa motility using Gaussian mixture model and matching based algorithm. Next. This is the result of the research we have done in the form of a table. Next. So we have some room for improvement. First, the traditional method of analyzing sperma quality labor-intensive and time-consuming. The require manual evaluation by highly trained specialists, which introduce the potential for human error and variability in result. Additionally, this method often hampers by data scarcity, as acquiring large, high quality data set is both challenging and expensive. Another significant issue is the sensitivity of this traditional method to environmental factors, such as vibration and inconsistency in sample preparation. This factor can lead to inaccuracies and on reliable result. Our goal is to develop um, robust automated system that overcome the challenger by leveraging advanced machine learning technique such as Western generative adversarial network and transfer learning. By doing so, we aim to improve the efficiency, accuracy, and reliability of spam quality analysis, making it more accessible and dependable for clinical use. Next. To address the limitation identified in previous studies, we propose using data augmentation and in conversion advanced machine learning methods by utilizing the modified human sperm morphology analysis and applying interpolation, we can generate more comprehensive training data. This approach aims to overcome data scarcity and enhance the performance of our model. Next. This will be explained by assistant Daniel. Please, Daniel.
So I will continue the explanation from Mr. Gede Susrama. My name is Daniel, and today I will continue the explanation. So Mr. Gede explained before that we use HSMA as our data set. So initially we had a comprehensive set of data in the form of videos for sperm analysis. Unfortunately, this valuable asset was lost. So as a result, we have had to rely on the MHSMA dataset while we are in the process of collecting a new dataset. The MHSMA dataset is a collection of images from 235 patients with male factor infertility. We choose MHSMA because each image is labeled by expert for normal or abnormal sperm acrosome, head, wall, and tail. The training set contains 1,000 images. The validation set contains 240 images, and the test set contains 300 images. So these images are available in two different crop size in 128 times 128 pixels, also 64 times 64 pixels. But we have new problem because the data form of MHSMA is a NumPy array. So interpolation plays a crucial role in converting the MHSMA datasets NumPy arrays into usable image data. This process allows us to upscale and downscale images, creating a larger and more diverse dataset. So let's see through this flowchart, which outlines the process of reading NumPy array file, displaying images with different interpolation methods, and saving them. The first step is to read the NumPy array file that contains the image data, and next we set the directory path where the process image will be saved. And after that, we initialize a counter variable count to 0. And this will help us keep track of the number of images processed. We then enter a loop that iterates through each pixel in the image, and the condition checks if there are more pixels to process. Display image with desired interpolation. For each pixel, the image is displayed using the desired interpolation method, and the three common interpolation methods shown here are nearest neighbor, bilinear, and bicubic. And after displaying the images, we increment the counter by 1, and the process image is then saved to the specified directory. We increment the pixel index I by 1 to move the next pixel, and lastly, the loop continues until one child pixel are processed and the flowchart ends. So even with that process, we found out that we only can generate approximately 5,000 data images. And the documentation is essential to address data scarcity. Techniques such as flipping and rotating image help the model recognize sperm in various orientation. Additionally, certain generative adversarial networks, or WGAN, generate high-quality synthetic images, expanding our training dataset and improving model robustness. So here we see the workflows for different augmentation technique. Flipping and rotating images provide diverse positional examples, enhancing the model's ability to accurately recognize sperm cells in real-life scenarios. And we have WGAN to generate synthetic images that closely resemble real ones, effectively expanding our training datasets. Then by integrating the synthetic images, our model gains a broader understanding and becomes more capable of accurately analyzing sperm quality. These augmentation are critical in overcoming data limitation. So we have a flowchart that provides a systematic approach to flipping and rotating images in order to augmentation. The first step is to retrieve a list of all items in the specified directory, and this directory contains the images that we want to process, and then we enter a loop that iterates through each item in the directory. The condition check if there are more items to process. For each item, we check if it is a PNG image, and if the item is not a PNG image, we skip it and move to the next item. Otherwise, we proceed to the next step. Then we read the PNG image into memory. The image then flip horizontally, and this means that the left and the right sides of the image are swapped. We increment counter variable. This counter keeps tracks of the number of images that have been processed, and the flip image is saved to the directory or to specified location. Also, we check if there are more items to process in the directory, and if there are more, we look back to step 3, and if there are no more, then the process ends. So we will do the same for rotation, except we will use rotate instead of flipping. So multiple position augmentation give our model more examples to learn from without needing extra data, and this helps the model become better at recognizing sperm cells from different angles and position, making it more accurate in real life situation. So this flowchart outlines the process of training Western Generative Adversarial Network, or WGAN, and evaluating it using the Frechet Inception Distance, or FID score. The process begins with two inputs, real images and noise. The real images are samples from the actual data distribution, while the noise is a random input used to generate fake images. Then, the noise is fed into the generator, which produces fake images. Then both the real images and the generated fake images are passed to the critic, or also known as the discriminator, and then the critics evaluate these images to distinguish between real and fake ones. This loss measures how well the generator is producing realistic images and how well the critic is distinguishing between real and fake images. Based on the calculated loss, both the generator and the critic are updated to improve their performance. The generator aims to produce more realistic images, while the critics aims to be better distinguish between real and fake images. The steps involves tuning the hyperparameters and running multiple epochs to optimize the performance of the WGAN. So each epoch represents one complete pass through the training dataset, and once the training is complete, we move on to the evaluation phase. After the training is complete, we generate a new set of fake images using the trained generator, and both the real images and the newly generated fake images are passed through an inception model to extract features. The inception model is a pre-trained neural network that provides a high representation of the images, and the extracted features are used to calculate the mean and covariance for both the real and fake images. And then the Fredset distance is computed between the distribution of the real and fake images. This distance measures how similar the two distributions are. The computed Fredset distance is the FID score. A lower FID score indicates that the generated images are more similar to the real images, signifying better performance of the WGAN. So what to do next? Before we use the dataset and train the model, we need to label each data point as either normal or abnormal so that the model can learn from it. The HSMA dataset consists of images showing individual sperm heads, while the FISM dataset contains videos of multiple sperm cells within a single microscope view. This result is in different bounding box size and dimension for each dataset. So before training our model, it is crucial to label each data point as normal or abnormal, and this involves annotating of both images and videos using tools like Label IMG and open labeling. Proper annotation ensures that our models learns effectively from the datasets. So firstly, the system opens the video file that contains the footage to be processed. The first frame of the video is read and processed, and then we select a bounding box around the object they wish to track. And then the KCF, or kernelized correlation filters tracker, is initialized with the selected bounding box. The system enters a loop to continue tracking the object in the subsequent frames, and then a new frame from the video is read, and then the tracker is updated with the new frame to continue tracking the object. And finally, the system checks if the tracking is successful. If tracking is successful, draw bounding box on frame. The bounding box is drawn around the track object in the current frame, and then display the frame. The current frame with the bounding box is displayed. If tracking is not successful, then pop up a message indicating tracking failure is displayed. So then the loop is broken if the end of the video is reached or if tracking is no longer required. If video capture is released and any of the windows are closed, then the process ends. So model development and the problem. Developing accurate models for sperm quality assessment is challenging due to the need for extensive training data and computational resources. Traditional methods are time-consuming and costly, and achieving high performance with limited dataset remains a significant hurdle. So the approach to this challenge is we utilize a transfer learning approach, and this technique will allow us to leverage pre-trained models which have been trained on large-scale datasets and fine-tune them on our specific sperm quality dataset. This approach significantly reduces training time and improves model performance. So transfer learning enables us to benefit from features learned from large-scale datasets by fine-tuning this pre-trained model on our specific dataset. We can achieve higher accuracy and efficiency in sperm quality analysis. So for models that we use, we employed MobileNet V2, MobileNet V3, and EfficientNet models due to their proven efficiency and high performance in similar tasks. Each model offers unique advantages, making them well suited for our application. So in model configuration, we have four category, like these features: MobileNet V2, MobileNet V3, and EfficientNet. So the introduction year, MobileNet V2 is introduced in 2018, MobileNet V3 in 2019, and EfficientNet in 2020. The purpose is in MobileNet V2 is for efficient neural network for mobile and embedded. In MobileNet V3 is for improved efficiency and accuracy for mobile. And then EfficientNet is for object detection with scalability and efficiency. So core innovation The core innovation is for mobile V2 is inverted residual, linear, and bottleneck. So mobile V3 for squeeze and excitation, blocks and hard twist, and efficient that is by FEN and compound scaling. Okay, we move on to the architecture review overview. So mobile V2 is an advanced version of the mobile architecture designed for efficient neural network operation on mobile and embedded devices. It builds upon the original mobile by introducing several key innovations that significantly improve performances and reduce computational complexity. So below it is the description of mobile V2 architecture. The first one is in the input layer. The network takes an input images typically of size 224 times 224 times 3. And then the initial convolution is a standard convolutional layer with patch normalization and ReLU 6 activation function. And the bottleneck blocks contain each block that includes the first one is expansion. It's point-wise convolution to increase the number of channels. Depth-wise convolution for applies convolution independently to each channel. Projection for point-wise convolution to reduce the number of channels. And then residual connection adds the input to the output of the block when the dimension match. We move on to the next architecture that we use is mobile V3 as a convolutional neural network architecture specifically designed for mobile and edge device application, prioritizing both efficiency and performance. It is the latest iteration in the mobile net series, which has evolved to provide better accuracy and efficiency. So mobile feature includes initial convolutional layers followed by a series of bottleneck layers with various kernel sizes and expansion factors. It also includes squeeze and excitation blocks and edge squeeze linearities for efficiency. So looking ahead, we plan to refine our models further and expand our dataset with more diverse and high-quality images. We aim to integrate additional data augmentation technique and explore new machine learning algorithms to enhance our model's performance and accuracy. So the conclusion for this presentation is this project focuses on building a model to automate spark quality analysis using MobileNet V2 and V3 and efficient data. The scarcity of sperm data can be addressed through augmentation technique, and this technique involves generating synthetic data using GAN algorithms and applying object position transformation. So thank you for the attention, and we open to any discussion and any question for viewers. Thank you very much.